Welcome, everyone. Happy New Year to the January 7, 2022 meeting of the Memphis Astronomical Society. I'm your host, Jeremy Veldman, and once again, we've got an excellent program for you. You probably followed the news, Christmas Day, the successful launch of the James Webb Space Telescope, and tonight we have a professor who has reserved time on the James Webb Space Telescope, professor of astronomy and physics right here in Memphis, who's going to be talking about some of the exciting research he's going to be doing with the James Webb Space Telescope. So stick around. You're not going to want to miss this meeting. But before I get started, just a few preliminaries. You can enable sharing, Rick.
Okay, go ahead.
All right, first of all, we are the Memphis Astronomical Society. And again, we are a nonprofit public service organization promoting interest and education in astronomy and related sciences. You can check us out on our website, memphisastro.org. We got a Facebook group, and of course, we're on YouTube. So if you haven't already, please take a minute to subscribe to this YouTube channel. Once again, I want to say a special thank you to all our subscribers. Hope you get a lot of value out of tonight's meeting. On our website, if you'd like to be added to our email distribution list, you can do that by clicking the join button, both in the upper right, and the lower right. Just click the join button. That will take you to a separate form. And of course, all you have to do is just fill out your details. And we send out notices, again, about once a week regarding upcoming events, whether they're regular meetings like this one or public outreach and observing events. So if you'd like to be on our email distribution list, just go to our website, memphisastro.org, and click the join button. You can also go into joinmas.com and enter your name and email that way. But probably the best way to do it is just to go to our website, memphisastro.org. But either way, that's how you engage with us and get on our list. Calendar of events. So we got quite a few things coming up this month as far as observing and outreach. And so I just want to make you aware of what we've got going on. And once again, Happy New Year to everyone. Hope everybody had a happy, safe, and enjoyable holiday season. And as BB King is famous for saying, now we get the next 6 months to pay our bills and get caught up by June. With that said, but yeah, hey, we're in the astronomy profession, right? So here's what we got coming up. Most of it is toward the end of the month. So the next week, not a whole lot is going on. We have a waxing moon, so we're getting close to the full moon about mid-month or so. Now, tomorrow night, we were scheduled to be at Shelby Farms for regular observing. It does look like that event is going to be clouded out. And for the foreseeable future, it looks like we're going to be suspending our outreach events at Shelby Farms. There were some issues with P1 or P5 parking area where we normally would meet. And I'll spare you the details. It has nothing to do with our group, but there's been some reports of vandalism and extracurricular activity. So they have to close the gate. So that area is no longer available to us. We will be discussing alternative venues at the upcoming MAS board meeting. But for now, what we've done at Shelby Farms is temporarily put on hold. So, and again, we'll probably be clouded out tomorrow night anyway. Now, January the 22nd, again, after the full moon, we get into the latter stages of the moon. We plan to be at Burton's for our regularly scheduled dark sky observing sessions. So that's coming up January the 22nd. That's 2 weeks from tomorrow. Now, the following week, which is basically the last week of January, we've got several things coming up. So Jeter Elementary reached out to us, and they're having their space week that week. And they've requested our services on Tuesday, the 25th. And again, Jeter Elementary is near Meeman, Shelby Forest State Park. So I plan to be out there. A couple other board members have reached out, members of the outreach team. But bottom line is, this is an opportunity, if you have a scope, to come on out and participate. So we will be reaching out to several of our faithful observers and requesting their services Tuesday, January the 25th. And the rain date is 2 days later, the 27th. That's a Thursday. So we got 2 shots at the Jeter Elementary Space Week. And this is a great outreach event for kids. So tentatively circle your calendar if you're available and you have a telescope for either Tuesday, the 25th or Thursday, the 27th, whichever night is clear. So that's last week of January. Now, the following night, Friday, the 28th, we are scheduled to be at the Museum of Science and Industry. I'm sorry, Museum of Science and History, MOSH, which is also the Pink Palace. So we've done events for them. So again, that's Friday, the 28th. That's the last Friday in January. You have a telescope and you can come on out. And of course, if it's clear, then tentatively plan on that as well. The following night, which is the last Saturday in January, the 29th, we have another dark sky observing session scheduled at Burton Sugar Farm. And a group of us is going out to Pinecrest campgrounds in Moscow for an observing event out there. So they will have an indoor program, not by the MAS, around 5:30, and then 6 or 6:30 or so, people will come on out and look through our telescopes. So that's January the 29th, Pinecrest Camp. And again, we only need a handful of people, maybe 5 or 6 telescopes, and we'll reach out to certain individuals. But if you're available and you're interested that night, reach out to us. And again, we'll be reaching out to some of you as well, requesting your services. But there's a lot of stuff going on toward the end of the month, really the last 2 weekends of January. So that's what we've got coming up. And we will, again, send email notices out as we get closer to these dates. And again, it's all weather pending. So whether the skies are clear or not, we always make the observing call that day, whether, depending on the weather. So, but if you're available and if you're interested, just tentatively plan on those dates, essentially January the 22nd to the 29th. So that's what we've got coming up. Okay, and again, if you're interested in outreach from the MAS, there's a form on our website. Just click on Schedule Talks/telescopes in the upper right, and there's a form that you can fill out. I'd like to get as much information on the front end as we can so that we have details in how we can service your needs for your group, whether it's telescope operators or presenters or both. So we're in for another busy year, I can already tell. So, but yeah, that's how you engage us if you have a group that's interested in the services of the Memphis Astronomical Society. So whether it's, again, presentations or telescopes or both. So go to our form, go to our website and click on Schedule Talks/telescopes in the upper right. All right, I want to announce some new members. And once again, I'm not going to put anybody on the spot. I'll just mention you and want to extend a welcome to the group. Dairo Jones, who was approved last month on December the 16th, as well as Robert Jones, who was approved December 26th. Arnetta Pender, approved December 27th. And Chuck Garner, who was approved on December the 30th. So again, I want to just extend a virtual hand clap and welcome all of you to the Memphis Astronomical Society. We're very happy to have you on board as a part of our community, and looking forward to meeting you at a future outreach event, and hope you get, again, a lot of value out of being a part of our community. And if you're a paying member, you get access to the Meteorite. I will send this out again because I realize some of you just joined our group. So if you didn't get this month's issue of the Meteorite, I'll resend it again. There's a couple of good articles in there, one especially on the James Webb Space Telescope. So one of the perks of being a member is you get access to our newsletter. All right, a couple of observing updates here. Hopefully, we haven't had many clear skies, certainly recently, but for those of you who have gotten out recently, hopefully you've been able to take advantage of some of the nice weather we've had prior to the last couple of days. But just to kind of orient you here, this is a view from Hernando Point Campground at Lake Arcabutla from a few nights ago. And there's the planet Jupiter right there, and Saturn right there. If you look low on the horizon, a very thin 1-day-old sliver of a crescent moon. and then a dot right there, which is the planet Mercury. And then below the horizon already set was a crescent Venus. So this was a pretty spectacular night of viewing. I love this spot. Once in a while, Brian will drag me out here, and it really is breathtaking, especially in either December or January. So this was a pretty cool night for observing. And you can see we took a couple of photographs of the, again, 1 day old, very thin sliver of a crescent moon. And I also had a view of some of the planets. And Brian took a shot. We also looked at the Sculptor Galaxy, NGC 253, as well as the globular NGC 288, which is right near it. And I actually got a little bit of a taste of astrophotography, taking my very first image with a DSLR camera. Orion rising through the trees. Got a long way to go, nowhere near the level of some of our experienced veterans, but it was a great night to be sure. And of course, our last look at Comet Leonard for quite a while. I don't know when it comes back around, but we were very fortunate both in December and January to have a couple of shots at viewing Comet Leonard. Not nearly as spectacular as Comet Neowise from a year ago, but still pretty good. So yeah, check out a video of this on our YouTube channel. And hopefully, again, some of you have gotten out and taken advantage whenever we can of some of the clear skies. Also want to give a shout out to my main man, Will Young, Deep Sky Dude. And he's got a YouTube channel also with some very informative videos. And these guys are in Texas. Will Young is the president of ASSET, which is the Astronomical Society of Southeast Texas. And I want to point your direction to this video right here. They just posted it. It was a live stream from a couple of nights ago. And basically, it was a conversation between Will and Joe Califf, who's the president of the Houston Astronomical Society, talking about some of the equipment that they got over the holidays, as well as some of the equipment that they use for both observing and astrophotography. And they cover eyepieces, telescopes, cameras, answer questions. They actually talked about the James Webb a little bit too. So pretty good video. If you're looking for some more information on equipment and maybe some tips, then this might be a good video to check out. I've always appreciated their production. They've got a good group and looking to do some more collaboration. Got some exciting things going on in Texas. A lot of star parties there as well. The Texas Star Party, El Dorado Star Party. So anyway, if you're looking for your additional astronomy fix beyond what we can provide, check out his channel and check out that video as well. I think you'll get some good value out of it. Okay, and that leads us to our program tonight. And our presenter is a professor, assistant professor in the Department of Physics and Material Science at the University of Memphis, Dr. Muller Sanchez, who has approximately, I think, 28 hours of reserve time on the upcoming James Webb Space Telescope. And really, that's all I would need to say for tonight's introduction, hopefully. But I'll just read a few things about our presenter tonight, and then I'll turn over the program to him. Professor Muller Sanchez is an observational astronomer with a broad interest in extragalactic astronomy. His research focuses on galaxy formation and evolution, with interests ranging from the physical properties of active galactic nuclei and nuclear star clusters to the role of supermassive black holes in galaxy evolution, galaxy mergers, and the cosmic evolution of the relations between the central black hole and its host galaxy. He uses multi-wavelength analyses for these studies with a focus on the optical / near-infrared and radio regimes. Dr. Muller Sanchez joined U of M's physics department in the fall of 2018 to help expand the astrophysics program. Through the introduction of new astronomy and astrophysics courses over the last year, the University of Memphis now has an astronomy concentration as of the spring of 2019. So if you're a young person in the Memphis area and you're watching this presentation, I just want to make a note that there are opportunities for you right here in the Memphis area. You don't necessarily have to leave to pursue a career or an academic education in astronomy. So keep that in mind. We have some excellent programs through our universities right here in Memphis. Dr. Muller Sanchez received his PhD degree in physics and astronomy from the Ludwig Maximilians University in Munich, working at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. Prior to his arrival in Memphis, he spent 3 years as a postdoctoral fellow at the Instituto de Astrofísica de Canarias, IAC, in Spain, 2 years as postdoctoral fellow at the University of California, Los Angeles, UCLA, and 5 years as research associate at the University of Colorado, Boulder. So with that, ladies and gentlemen, please help me give a warm welcome to our presenter tonight, Dr. Francisco Muller Sanchez.
Okay. Thank you, Jeremy, for this very nice introduction. And thank you for the invitation to speak today at this meeting of the Memphis Astronomical Society. I'm happy to see that you are very active. You have a lot of things going on. This is my first time in one of these meetings, so I'm very excited to hear more about the things you do in the future as well. Actually, I have to say that we met, we met at the University of Memphis a few years ago, but we talked at the last observing meeting at the Pink Palace, or the Mosh, as they call it right now. And I think there we can have a nice experience observing, because my students and we will be joining these observations at the Pink Palace, and I'm hearing that you will be also participating in those. So I probably will see more members of the Memphis Astronomical Society there as well. Okay, so today I'm going to talk about the James Webb Space Telescope. So I would like to share my screen with you. I don't know if I can do that now. Share screen. Okay. Yeah. Okay, here we go. All right. So as you all know, and I heard you were actually talking about that at the beginning of this meeting, the James Webb Space Telescope was successfully launched on December 25th, 2021. So it's last year now. And in the astronomical community, we were all very excited that night, so Christmas Eve and Christmas Day, because this is a project that took many years to be able to finally see the telescope launching into space. As you probably know, the James Webb Space Telescope is the most ambitious project in the history of NASA. If not in all areas, it is certainly the most ambitious astronomical project in the history of NASA. And the reason is because it is the largest space telescope ever built. So it has a diameter of approximately 6.5 meters. And this is the largest space telescope ever built. So that alone makes it the most ambitious astronomical project in the history of NASA. But also all the technological developments, the instrumentation on board of James Webb, and all the aspects related to the telescope makes it also a very challenging project. So that's why I remember that when I started my PhD in Germany, approximately 16 years ago. I mean, as you probably know, it was delayed many times. Of course, the cost of the telescope also increased exponentially. So it was much more expensive than it was originally planned. So all those things make it a very special telescope. And that's why we were all very excited and very nervous on December 25th. And now it's a little bit more than 10 days since the launch. And we are also checking every day what is going on with the telescope. Unfortunately, I can tell you that everything is going well. And in fact, there are things that are better than we expected. So those are the things that I would like to discuss with you today. So my talk is divided into 3 parts. The first part, I will just talk about some basic information, some characteristics of the James Webb Space Telescope. And then in the second part, I will talk about the current status of the telescope after the launch. And then in the last part, I will talk about the science that I am planning to do with the James Webb Space Telescope when we start collecting data. Probably will be during the summer of this year. Okay, so I mentioned many things that make James Webb very special, but I think, of course, the most important thing about this telescope is that we will be able to do science that we couldn't do before in the past. So this year, we're going to hear a lot of, this is the first time that we, and then you can add many sentences after that. There will be many first times with this telescope. Actually, in the community, we expect that James Webb will revolutionize our understanding of the universe in the same way that Hubble did 30 years ago, approximately. So there are many areas that will be studied, many areas in astronomy that will be observed and studied with James Webb. But some of the most exciting things are mentioned here. So it's a telescope where we will be able to discover light from the first galaxies in the universe, and we will be able to explore distant worlds and what we call extrasolar planets. But like I said a few minutes ago, this is an all-purpose telescope that it will be used by thousands of astronomers worldwide and for all areas of astronomy, going from planets in the solar system or objects in the solar system, including comets, asteroids, planets, etc., to the most distant galaxies in the universe. And as Jeremy mentioned, an example of concrete science project that will be done with James Webb is the study of supermassive black holes. So that's my research project, or my 2 research projects that were accepted for observations with the James Webb. And I will talk about that in a few minutes. So this, as you probably know, is a project that is led by NASA in partnership with the Canadian Space Agency and the European Space Agency. So before we talk about the science that we can do in more detail, where does the name come from? Who was James Webb, right? That's the name of this telescope. So here you can see some of the important things that James Webb did as an administrator of NASA. He was the second administrator of NASA. But in my opinion, the most important contribution and the reason why this project is called James Webb Space Telescope is here in the last point, is because he insisted that NASA should have a strong science program. So before Webb or during the time of Webb, NASA was developing a lot of instrumentation technology, space vehicles, rockets, etc. But the amount of projects related to science or pure science, natural sciences, was limited. So James Webb insisted that NASA should have a very strong science program, and that's what actually NASA does now. I mean, it's involved in many aspects, but it's mainly an institution that does science, and it does all types of science, natural science, physical sciences, and of course, astronomy and astrophysics. So that's why some scientists decided, or they pushed for this name, for this telescope, the successor of Hubble, basically. You know, James Webb is considered the successor of the Hubble Space Telescope, although in many aspects is different, as we will see in a minute. But like I said, we expect that it will revolutionize our understanding of the universe as Hubble did approximately 30 years ago. So what will Webb do? Like I said, we will study all the objects in the universe, or as it says here, every phase in the history of our universe. So in these 4 panels, you can see some examples of the exciting science that will be done by Webb. We will study the light from the first galaxies that were created in the universe after the Big Bang. So this will be the end of the dark ages. Then we have in the second panel, the assembly of galaxies. So my research projects are included in this part where we study galaxy evolution. So once galaxies formed, how did they evolve? How did supermassive black holes form? And how did they move to the centers of galaxies? As you know, in astronomy, we believe that all massive galaxies in the universe have a supermassive black hole at their center, but we don't know how this black hole was created or how it moved there in the history of galaxies or galaxy evolution. And also, this topic includes the coevolution of supermassive black holes and galaxies. So how supermassive black holes are fed by gas or the material in the host galaxy, which is a process that we don't know how it happens very well. And at the same time, how supermassive black holes influence their galaxies. As we know, there are many aspects, observational facts that we see in galaxies that cannot be explained without the presence of a supermassive black hole. So those are the things that I am studying, and that is part of this topic of assembly of galaxies. Then we have the birth of stars and planets, or regions where the stars are formed, and also new planets like young stellar disks. And finally, planets in other solar systems or extrasolar planets. And this is a very exciting topic because Webb will be able to characterize for the first time many extrasolar planets. So with the Kepler mission, we were able to discover thousands of extrasolar planets. I mean, it was a very successful mission, and we have more than 7,000 extrasolar planets in the vicinity of the solar system. But right now in the community, we think that the next step is the characterization of these extrasolar planets. Maybe not all of them, because it's not possible to do a characterization of all these planets, but some of them. And of course, already there are many science programs that are related to this topic, and that they have already selected some planets, extrasolar planets, that will be observed by James Webb during cycle 1 or during the guaranteed time observations. And we will start doing this immediately. And of course, this is very important because it could be that these first observations of extrasolar planets, they already provide evidence for life in other planets. So by studying the spectra of the atmospheres or the surface of other planets, maybe we will be able to detect already the organic molecules or some products of life that are related to living organisms. I mean, life as we know it here on Earth, or just the presence of liquid water on the surface of some of these planets will be a very important discovery for mankind and for the study of extrasolar planets. So, like I said, we are all very excited, and it could be that at the end of this year, we have a very strong evidence for life in another planet in the Milky Way. And if not this year, astronomers are very positive and very optimistic about the possibility of finding life very soon. If not, like I said, if not this year, maybe next year, or within the next 5-6 years, but certainly before the end of this decade. Okay. Now I was saying that James Webb is considered the scientific successor to Hubble, in the sense that it will study all the objects in the universe. There are astronomers all around the world that will use James Webb, as it was done with Hubble. And at the same time, there is some overlap in the wavelength range and the type of science that can be done. But as we can see in this table, Webb is much more powerful than Hubble. So we can begin by talking about the mirror, the size of the primary mirror. The diameter of the James Webb Space Telescope is 6.5 meters versus 2.4 meters of Hubble. So that already is an advantage and a characteristic of Webb that will give us the possibility of obtain a better spatial resolution for many of these objects that were observed by Hubble, and at the same time, more sensitivity. So as you know, the larger the diameter of the telescope, the more collecting surface area of photons that we will have, and therefore we can observe fainter objects, things that couldn't be observed by Hubble. Now they will appear for the first time with Webb. Then we have length and height. Well, I have a slide where we can compare these two parameters, but basically Webb is comparable to the size of a tennis court and Hubble is comparable to the size of a bus. So Webb is much more larger. Then in the wavelength of operation, Hubble had some instruments in the ultraviolet, the visible part of the spectrum, and the near infrared up to 2.5 micrometers. And Webb has a similar wavelength range in the optical and in the near infrared from 0.6 to 28.5 micrometers. But the difference here, as you can see, is that Webb will have instruments that will work in what we call the mid-infrared part of the spectrum. So from 2.5 to 28.5 micrometers, something that Hubble couldn't do. And of course, Webb does not have an ultraviolet instrument. So that is something that Hubble will still be doing. So astronomers who are experts in ultraviolet, they will still be using Hubble. And in fact, Hubble has right now what is called the UV initiative. Well, this has been going on for the past 4 or 5 years now, but it's just motivating the astronomical community to use Hubble to do observations in the ultraviolet, because when Hubble stops working, then we will not have an UV telescope. So we are still good with Hubble for the next 5 years, maybe. I mean, I don't know how long Hubble will still work, but then we will not have an UV space telescope probably for the next 10 years or 15 years, I don't know. But the things that we can do in the mid-infrared with this telescope, with the size of this mirror and from space, it's revolutionary. There hasn't been any other telescope in the history of mankind that could observe between 2.5 or even from 1 microns till 28.5 microns, the near infrared and the mid infrared at this resolution and at this sensitivity. So there is some overlap with Hubble there, but as I mentioned, due to the size of the telescope, Webb will observe much more objects that were too faint for Hubble and with much better spatial resolution. Now, the location, Hubble is located in an orbit near the Earth at approximately 570 kilometers from the Earth, but Webb will be located in an orbit that is at 1.5 million kilometers from Earth. That is the location of the L2, the Lagrange point number 2. So I will come to that in a few minutes when I talk about the journey of Webb from Earth to its orbit, where it will be working for the next, hopefully for the next 10, 15 years. And that is some very good news that we just heard in the past 10 days. But I will talk about this orbit in a few minutes. But this is, immediately you can see that this difference in the orbit means that with Webb, we will not be able to do service missions as we did with Hubble. So that is one of the reasons why we are all very nervous about all the different deployments and all the things that have to occur from after the launch and when it arrives to its orbit, to the L2 orbit, because many things have to happen. Unfortunately, everything is going well, as I said at the beginning of my talk, but this journey is still another 20 days approximately. So there are many other things that have to happen until Webb reaches its orbit. But once it's there, it's a very stable orbit. And that's why, I mean, it's out of our hands. We cannot do service missions, but we think that everything will go as planned as it has been until now after the launch. And finally, the temperature, because this is a mid-infrared telescope, as I mentioned a few minutes ago, it has to be cooled down. It has to work at temperatures of approximately 70 kelvins or less, so that we can observe in the mid-infrared. And that's a big difference with Hubble. Hubble worked basically at ambient temperature at 21 degrees Celsius. But like I said, Webb will be cooled down to less than 70 Kelvin, so to minus 230 degrees Celsius, which is approximately 40 Kelvins. So that will be the temperature of operation of Webb. So I was talking about infrared light. I don't think I need to describe in detail what infrared light is. It's just one part of the electromagnetic spectrum that includes objects with temperatures that can be considered cold, I mean, in the universe, from approximately 100 kelvins to 1000 kelvins. And this range of temperatures covers what we call the near infrared, from 1 microns to approximately 600 microns, which is the far infrared. These are objects that are not stars, or at least the peak of the emission. I mean, if we consider the emission of a star as a black body, it does not occur in the infrared. So 1000 kelvins are cooler objects. That's why we call this the warm universe or the cold universe, although it's not that cold, right? I mean, 500 kelvins or 1000 kelvins is not that cold, but it's not the temperature of the peak of the emission of the stars. However, because of this property of electromagnetic radiation and the black body emission, there is a lot of emission from the stars, especially at near infrared wavelengths between 1 to 2.5 microns. So we will see also a lot of stars which are emitting close to the red part of the spectrum, or the visible part of the spectrum, and that its tail in the black body is still in the near infrared, and they are very powerful. So one of the advantages of infrared light is that it's light that corresponds to temperature of objects, like I already mentioned, at 500 kelvins or 400 kelvins. So we are going to see new structures in, around the stars, around solar systems, around galaxies that have those temperatures. So things that we didn't observe before, at least not at this resolution and with this sensitivity. So this is mostly gas and dust, but it's also infrared light can see through fog and dust. So we can see the emission from the stars, like I said, that are at 1000 kelvins, approximately the tail of the black body spectrum that corresponds to those wavelengths. So that's why in many aspects, this part of the electromagnetic spectrum is considered the thermal part of the electromagnetic spectrum, because it is what corresponds to the temperature of humans or many other objects or living organisms also on Earth. I mean, temperatures of 300 kelvins, 270 kelvins, 350 kelvins, they are all in the near infrared, in the infrared. And that's why infrared light is considered heat, or by many people, this is considered the thermal part of the electromagnetic spectrum. And if we had an infrared camera, such as those that are in Webb, we will be able to see the gradients of temperature as it is represented in this slide. When we have water in a glass, or when we have ice and it's very cold, it's just emission at different temperatures that we interpret here as thermal emission. But like I said, this will open a completely new universe we will observe many new things at these wavelengths that have not been observed before. I mean, certainly not with Hubble. This is what I mentioned a few minutes ago. We have a comparison of Hubble versus Webb. So Hubble for scale was the size of a school bus, and now Webb is the size of approximately a tennis court. So in terms of collecting area or surface area of the primary mirror, the James Webb primary mirror is approximately 6 times larger than the Hubble primary mirror. And you can see here a comparison of the area, the collecting area of the two telescopes, Hubble versus James Webb, and how James Webb is much larger, which, as I said, it translates into a much better spatial resolution and much more sensitivity. We can collect much more photons with this telescope. Okay, the launch, which was a very exciting moment for many of us. As you know, Webb is so big, the size of a tennis court, that it cannot fit inside any of the rockets that we have developed by any space agency. So it was folded up like an umbrella. So many of the elements of the James Webb after launch, they had to be deployed, or Webb will just, or it's opening up like a transformer or like an origami structure, as we will see in the next slides. So this was a very big success. And now we have something that looked like this in space, not yet like this, because this is the telescope with all its instrumentation and all its components, but we are approaching this stage. So we can divide the elements of the James Webb Space Telescope into 3 parts. We have the optical telescope element, which of course corresponds to the primary mirror, the secondary mirror, and the backplane, which has all the optics. And then we have the spacecraft element that corresponds to elements of the satellite, of the vehicle, which includes the sun shield, the bus that has host structural communications and propulsion components. And finally, we have the instrument element, or the instrumentation, where we have, this is what you see right now in this animation. This is all the instruments on board of James Webb. There are 4 instruments. So cameras and spectrographs. There is a mid-infrared instrument, a near-infrared camera, a near-infrared spectrograph, and a fine guide sensor with a spectrograph as well. So I will just run this animation again so that we see. The first part, actually what you see right now, is what we call the spacecraft element, with the sun shield, the bus structure, the solar panels. As you know, James Webb is going to obtain energy from the sun using solar panels. So this is what you can see here, the sun shield that protects the optics and the instruments that, as I said, they have to be cold from the sun. So the gradient of temperatures between the part that you see right now here in the solar panel are under the sun shield, and the temperature at the telescopes is more than 200 degrees or 300 degrees. And this is something that we have measured that is happening right now, and it's working well. So that's one of the many successes. I mean, many of the things that have happened in the past 10 days, and that we know that they are working well. Okay, so we can see here the sun shield, the solar panels, and other parts for communications and propulsion components. And then as we move in the animation, we see the optical telescope element with the primary mirror, the secondary mirror, the backplane with other mirrors and lenses and optics. And finally, in the back of the telescope, we have the 4 instruments that I mentioned and that I'm going to describe a little bit more in detail in the next slides. But you can see them here right now. Okay, so with this slide, I mean, now I have only some pictures of the James Webb in the lab, so Webb testing, which now we are all very happy that it's working well. So here you have the primary mirror, the fully tensioned sun shield in the lab, which is something that just happened, as you know, a few days ago on January 5th. So a couple of days ago, this was a very important part in the deployment of all the elements of the telescope. And it was a very successful procedure, but this is a picture in the lab. So the telescope is like this now in space, but as you know, we don't have cameras, we cannot take selfies, and we cannot take pictures of the telescope right now in space. And these are the wings deployed, which has also been now opened up, and they are part of the telescope, and they work well. Okay, so now the launch and orbit. So Webb was successfully launched on top of an Ariane 5 satellite or rocket, sorry, on December 25th, 2021 from the French Guiana. And now it will undergo a journey for approximately 1 month until the second Lagrange point, which corresponds to approximately 1.5 million kilometers from Earth. So this is a very important image. Some of you, maybe you're familiar with this image. It was the last image of the James Webb Space Telescope that we could obtain from the Ariane 5 rocket before it decoupled the rocket and it started its journey into the Lagrange point. So this was the last image that was taken from the Ariane 5 rocket, and the telescope is moving away from the rocket. So after this, we will not see the telescope anymore, at least not in the optical with a camera, with a real image. So this is now a very famous image in the history of astronomy, the last image of James Webb after the launch. Okay, so the current status of the telescope, like I said, we are very happy because many things have happened and everything is going well. But there are 3 things that are, in my opinion, crucial for the telescope in its journey towards its final destination, and that happened in the past 10 days. So the first thing that I would like to mention here is that the James Webb will operate for longer than we hoped. And this is very good news. And this is something that we, of course, didn't know before the launch, because many things could happen during the launch. But this is mainly related, or mostly related, to the fact that we could save a lot of fuel or propellant during the launch that was not used, and that can expand the lifetime of the telescope by several years. So basically, NASA announced this news where it says that Webb's excess fuel will likely extend its lifetime. So I just highlighted here what happened. So basically, during the launch, and if you follow the launch or the video of the launch that is in YouTube or in many other social media, you could hear that the people were saying many times that the trajectory was nominal, and nominal many times. And if you follow the curve, the expected curve of the trajectory of the telescope to what the telescope was doing, it's a perfect match. So this means that we were lucky, and the rocket and the telescope didn't use too much fuel during its launch and after the first minutes after the launch. So NASA says that the observatory should have enough propellant to allow support of science operations in orbit for significantly more than a 10-year science lifetime. And here they also mention that the minimum baseline for the mission is 5 years. But now with this very good news, NASA thinks that it will work, or the lifetime of the telescope will be more than 10 years. We don't know how much more, but the fact that it says significantly more than a 10-year science lifetime is something that is making us very happy and very excited, because this could be maybe 15 years or maybe more. And that is very good news. So that is the first thing that I wanted to mention, something that happened after the launch. Now, the second important thing is that the first instrument has been switched on. So remember, I mentioned that there are 4 science instruments on board of JWST: NIRCam, NIRSPEC, MIRI, and NIRIS. And as the name indicates, actually 3 of these instruments work in the visible near-infrared part of the spectrum: NIRCam, NIRSPEC, and NIRIS. NIRSPEC and NIRIS are spectrographs. NIRCam is a near-infrared camera, and MIRI is the mid-infrared instrument. And it has both a camera and a spectrograph. So this instrument is the first one that has been switched on, and the people in charge of this instrument, the people who build this instrument and who are right now, they must be very excited that the instrument is working, and they started to do some calibrations. So it's the first instrument that has been switched on. And for the other 3, we will wait until Webb reaches its final destination. But again, this is a very good news that we are receiving data. Or we are sending instructions and receiving data information from the first instrument, MIRI. And then the last of this very good news is that the secondary mirror has been deployed, which means that we finally have a telescope in space. So as you know, as I mentioned a few minutes ago, the telescope was folded up in the rocket, and it's been doing several deployments in the past 10 days. It's more than 100 deployments that have to happen until James Webb reaches its final destination. But there are some very crucial moments. And one of them occurred 3-4 days ago when the sun shield was fully tensioned. And then the last one of these crucial deployments was the deployment of the secondary mirror, is what you see here, which occurred 2 days ago on January 5th. So the image that you see here right now is what we believe we have in space right now. And this is now the telescope, because before the deployment of the secondary mirror, we didn't really have we have all the space vehicle, the sun shield, the primary mirror, more or less. But now with the secondary telescope, we can say that we have a telescope in space, and that it looks like this or something like this right now in space. So at this moment, I would like to show you a YouTube video. This is from NASA, where actually they show the nominal deployment sequence of many of the elements of the James Webb. So this is how it was launched. And you can see how it starts opening up. After 2 hours, we have a high antenna deployment. The sun shield palette deployment is occurred 3 days after launch. So we have 2 of them. And then we started with the sun shield. We had a deployable tower assembly. So all these things already occurred, and they were a success. So we are very happy about this. The sun shield membrane cover release, and then the deployment of the sun shield, basically. This is the mid-room deployment, as you can see, how it occurred after 6 days. And then the other side, and then we have a fully tensioned sun shield that occurred 7 days after the launch. And now what I said in my slide, this is the deployment of the secondary mirror. So the image I have in my presentation is actually a screenshot of this part, what is happening right now. Now, tomorrow, actually, tomorrow, Saturday, yes, we will have the primary mirror wing deployment. So what you see right now the primary mirror was folded up, and now it will open up during the weekend. And that's one of the last of these crucial steps that James Webb will do after the launch. So NASA says that after this weekend, so next Monday, if everything goes well, we will have a fully operational telescope in space. And the most crucial deployments have already occurred. So the last one of these crucial deployments will occur tomorrow and Sunday. And then there will be other, but they are, I mean, or at least they think they are not so risky or crucial as the ones that have already occurred and that will occur during this weekend. Okay. So, like a final destination point, very quickly, the Lagrange case, JWST will be located in L2, but there are 5 Lagrange points, and these are regions that regions in space that corresponds to locations where the gravitational forces exerted by 2 massive objects, in this case, okay, can you hear me?
Yeah, we can hear you now.
Okay, yeah, I think I lost connection. So I was just saying that these are regions in space where the gravitational forces of 2 massive objects are balanced by the centrifugal force that keeps the object in orbit. So basically, it is like the parking spot of objects in the solar system. So if we consider the system of the sun and the earth, we have 5 Lagrange points where we can park their satellites or whatever we want, because the object is not going to lose angular momentum and spiral in towards the sun or towards the earth. So that's the characteristic of these points, that every time you have 2 objects, in this case, the sun and the earth, you have 5 points. But for example, the system Sun, Jupiter, those 2 objects, they also have 5 Lagrange points, or Sun, Saturn, etc. So we are interested in the Lagrange points of the Sun-Earth system, and L2 is a very good choice because it's further away from the sun, and that is something that is desirable for this mission because we will receive less heat from the sun. Also, the part that is looking to the sun, where the solar panels are, they will be at the relatively high temperatures. I mean 20 degrees Celsius, 50 degrees Celsius, which is much higher than the telescope itself, the primary mirror, the instruments, which, as I said, they have to be cooled down to minus 200 kelvins, sorry, minus 200 degrees Celsius or 70 kelvins. But we do not have contributions from thermal emission from the Earth, which is something good for this mission. And the other thing is that the characteristic of this orbit, like I said, is an stable orbit, so the object does not spiral towards the sun or towards the Earth, so we need less fuel. So objects that are in the L points, satellites, when we design the mission, we plan for a certain amount of fuel that is less than if it was located in any other part of the solar system. So it's also very efficient in terms of saving fuel. And finally, at this location, we are not very much obstruct. It will be very efficient for observations because we will not have the Earth that will interfere into planning of the observations, which was something that happened a lot with Hubble. So planning observations with Hubble was a difficult task that required 3 or 4 astronomers working only on that, or more people. And this, with this telescope, we have an unobstructed view of the universe on one side that facilitates operations. Of course, we cannot see objects that are in the direction of the sun, but everything that is behind, I mean, we will be able to observe all the time, and we can plan, I mean, it will be easier to plan observations of the several programs that will be observed by JWST. So that's also an advantage. Okay, so with this, I finish my talk about the James Webb Space Telescope. These are only some web pages of NASA, I mean, social media where you can follow Webb. In fact, I just saw that somebody shared in the chat a link where we can follow the current status of James Webb. I mean, it's live, and it is telling us where it is, what are the conditions of the space vehicle and the telescope. And that is where you can see the gradient of temperatures, where you can see that on the warm part of the space vehicle, the part that has the solar panels, it has a much higher temperature than the part above the sun shield, so where the mirrors and the optics and the instruments are located. And that gradient of temperatures is more than 150 degrees Celsius. So that's a very good sign already. Okay, so now I will start with the third part of my talk. This will take, I think, only 5 to 10 minutes more. And this is related to the science we do at the University of Memphis. Like Jeremy mentioned, we have an astronomy concentration at the University of Memphis, and we have students that are working, I mean, we have both undergraduate and graduate students. So we have students that are studying physics, but taking astronomy as a concentration. And then we have students who are pursuing a master or a PhD in astronomy. And they are all working in topics related to the evolution of supermassive black holes and galaxies. That's my research, and that's what I do. And I'm going to use Webb to do this. So as I mentioned a few minutes ago, and this is something that actually Hubble discovered or confirmed 30 years ago, is that supermassive black holes are found in all massive galaxies. So before Hubble, we had some idea. I mean, we had some measurement, we had some observations. People were talking about supermassive black holes at the centers of galaxies, but we had a small sample, or we had only a few objects where this was confirmed. I mean, maybe a few hundreds, but that's a small sample. And then thanks to Hubble, with observations of thousands of galaxies, 10,000s of more, we were able to confirm that supermassive black holes are found at the centers of all massive galaxies. And with Hubble, we were able to study the morphologies. I mean, in fact, what you see right now is a Hubble image of a galaxy with an active supermassive black hole. That's why you see these radio jets and ionized gas coming out from the plane of the galaxy. But Hubble was limited in terms of the instrumentation, specifically in terms of spectroscopy. So Hubble has a couple of spectrographs that work very well, and they did a great job, but they were not able to map the kinematics of objects. And that is something
Excuse me, Dr. Sanchez, you need to reshare your screen because you cut out and now we can't see your screen. So just reshare.
I'm sorry. Okay. Okay, thank you. Okay.
That's great. Thank you.
Yes. All right. Yeah. So I was just saying that this is a Hubble image of a galaxy with an active supermassive black hole. And with Webb, we will be able to study the kinematics of everything that you see in this image. So the kinematics of the stars, the kinematics of the dust, the molecular gas, the ionized gas, the highly ionized gas, all the species and all the components on galaxies. And this will be done for the first time with very high spatial resolution and with very high sensitivity. So the things that we will see with James Webb, I mean, we have, of course, some predictions, we have models, we have observations, but we expect to see new things that have never been observed before. An example of the things that we will be able to do is a confirmation of the masses of supermassive black holes. And that's why I show this slide, because as you know, the first supermassive black hole that was confirmed in the universe is the supermassive black hole in the center of the Milky Way, where Dr. Reinhard Genzel and Andrea Ghez, who received the Nobel Prize last year, exactly for these measurements that you see right now in the screen, they obtained the first confirmation of the existence of a supermassive black hole at the center of a galaxy, which in this case is the center of the Milky Way, our galaxy. So they observed with the Keck telescopes and the Very Large Telescope in Chile, the stars that are moving around the center of the galaxy. So what you see here in this animation, the red cross corresponds to the dynamical center of the galaxy or the kinematic center of the galaxy. And you see the stars, this is real data, real stars that are moving around that center of mass. And of course, there is nothing at the dynamical center of the galaxy. It's just black. I mean, there's no light coming out of the center of the galaxy. And in addition, this volume, it is very small. I mean, for comparison, you can see the size of the stars. These are all stars, and you can see how the size corresponds in this image. So when the stars move around the center, the center of mass occupies a very small volume, even smaller than the stars that are here. So these three facts, I mean, the fact that it's the center of mass is dark, it occupies a volume that it is very, very, very small. And if we apply the Kepler's laws of motion to the orbits of these stars, we will measure a mass of approximately 4 billion solar masses or 6 billion solar masses in that range. Million, sorry, I think I said billion, it's million. 4 to 6 million solar masses. And that is a huge mass. So you cannot, I mean, we cannot imagine any object or even a cluster of stars or neutron stars or whatever you can think of that will occupy that volume and that will create a mass of 6 million solar masses. So this is, like I said, the first very strong evidence that we had for the existence of a supermassive black hole in a galaxy. And with Webb, we will be able to do similar experiments to this. Probably we will not be able to measure the kinematics of individual stars, but we will measure the kinematics of star clusters. So several stars that are moving around the central region of the galaxy, and applying the same physics, Kepler's laws of motion and celestial mechanics, we can estimate the mass of the central object. And like I said, this will be done for many galaxies with high spatial resolution and high sensitivity for the first time. But the other very interesting topic that is related to supermassive black holes is basically try to understand their lives. So how did they form? How did they originate at the center of the galaxy? If they were smaller, I mean, assuming that they were stellar mass black holes at some point, how did they grow to the size from 30 solar masses to 1 million or 1 billion solar masses? How does that occur, that process? We don't know. We don't have a good idea of how supermassive black holes grow. I mean, we also don't know how supermassive black holes are formed. There are some theories, but there is no real observation or some observations that will definitely give us an answer to those questions. And also, we see, and that's the plot that you see in this slide, that there is a correlation between several properties of the stars. In this case, is the velocity dispersion of the stars and the mass of the supermassive black hole. This is called the M sigma relation. And like this relation, there are many. There are more than 7 or 8. And this is telling us that the black hole has influence on things that happens on galaxies. But as we know these facts and we know empirically these relations, we don't know why this happens and how this process occurs. So one of the theories, and that's what I'm studying in galaxies, is what we call supermassive black hole feedback, in which the gas that is orbiting around the supermassive black hole is actually expelled by the gravitational forces and the luminosity of the accretion disk of the black hole, and that creates or injects some mechanical energy to the interstellar medium of the galaxy, and that is what creates these relationships. So this is something that we are studying right now with ground-based telescopes, with Hubble as well, but we expect that with Webb, we will obtain a definite answer about how supermassive black holes influence their galaxies. So this is what I was saying about feedback and why it is very exciting and surprising, because we can do a scale comparison of the size of the black hole to the size of the galaxy will be comparable to something that is the size of a penny to the size of the Earth. And imagine that this penny, or this object that has the size of a penny, has a great influence on all the processes that occur on the surface of the Earth. And this is, again, something that we didn't know about this 30 years ago. Hubble played a big role in discovering these relationships, like the M sigma relationship that I mentioned, or all the other relationships. So this connection of the black hole with the galaxy, it is something that we talk about in the past 20 years, since 1999 approximately. And it was, like I said, thanks to Hubble. So now with Webb, we know that this exists, and now we want to explain why and how this takes place in galaxies in the universe. And finally, I'm also studying what I always say, these are the most beautiful astronomical images of the universe, which are images of galaxy mergers. And the reason why I say they are the most beautiful is because you can see what I call the cosmic dance of galaxies. And here I just show a collage of some of these galaxy mergers. These are all Hubble images of galaxy mergers, and you can see the different morphologies, or the beautiful morphologies and beautiful shapes of these galaxies interacting with each other. All of them are different, as you can see, and as you can imagine, depending on our line of sight, the angle that we are looking at the object, the angle of the interaction. Some galaxies are face on, others are edge on. The time of the interaction, some of them are early stage mergers or are late stage mergers, or in some of them, the galaxies have already merged, but the black holes haven't merged yet. So there is a lot of variety, and that's why I think, in my opinion, it makes this field very interesting, because all these mergers are different and all the images are beautiful. So in this area of astrophysics, I'm interested in understanding how the two supermassive black holes merge. And in this image, I'm showing some of my previous work where I studied the galaxy NGC 6240, which is a very famous galaxy merger with two active supermassive black holes. That's what you see at the center here that I call the northeast nucleus and the southwest nucleus. Those are the two active supermassive black holes. And the galaxy merger is huge. I mean, it occupies several kiloparsecs in the image, but this is assumed to the central region. And in the central region, you see this structure that people call the butterfly nebula. If you follow the green and red colors here, this looks like the wings of a butterfly. So with instruments in the Very Large Telescope and at the Keck Observatory, and using Hubble, this is a Hubble image actually of the butterfly nebula, I was able to dissect the butterfly. So that's what I did in this research. I separated all the regions of the butterfly and I studied the kinematics of the gas and the stars and the dust in each of these regions. And that's what you see here. This is a paper that was published in Nature in 2018. And what you see here, these are called velocity maps and flux maps. And something like this is what we will be able to do with James Webb, but with much better spatial resolution and with much better sensitivity. So this data, it took me several hours or even days at the telescope to collect the data and then to reduce the data. And as you can see, the field of view is still limited and I don't have the best spatial resolution because of the clouds in the atmosphere. But with James Webb, we will be able to do this, obtain very similar maps for many of these galaxy mergers. Basically, all these images that you see here, we will be able to study them with James Webb and obtain these maps. And of course, this is very important for our understanding of the process of galaxy mergers, how the gas and the stars as two supermassive black holes merge. And in the end, how these supermassive black holes actually produce gravitational waves. And that's a very important topic, not only in astrophysics, but in physics in general right now, to understand the production of gravitational waves. And models suggest that the two supermassive black hole mergers are the objects that produce the strongest gravitational waves in the universe, but we have never seen these occurring. So I have a project on board of JWST, or that will be observed with JWST, to observe a galaxy that it was, it's a galaxy merger, but it has a supermassive black hole that is not at the center of the galaxy. And there is evidence from ground-based observations that suggests that this black hole is actually a recoiling black hole, which means that in this galaxy merger, actually it's a merger remnant where the galaxy already merged and the two supermassive black holes also merged, but due to the very strong production of gravitational waves, the supermassive black hole, the newly formed supermassive black hole is kicked out from the center of the galaxy. That's what we call a recoiling black hole. And if my observations are successful and we do the measurements and we study the galaxy, maybe we will be able to confirm for the first time the existence of gravitational wave recoils, which is something very important because I will be able to say how the merger process occurred, what are the conditions of the two galaxies before the merger of the two supermassive black holes, and what are the expected gravitational waves produced by these galaxy mergers. So as you can see, I'm very excited about this project. I can talk a lot about this science, and it is something that I'm waiting in the next months. Hopefully they will observe my object and hopefully we can meet again and I can give you some good news about this. Okay, so this is my last slide. I will just leave you with the information of my research group at the University of Memphis, which is basically an observational extragalactic astronomy group, and some of the information of my CV and the things that we do. Thank you for your attention.
Thank you very much, Dr. Sanchez. Give a round of applause for an excellent and highly informative presentation. I know we've got several questions in the chat that we'll get to in just a second. Now, correct me if I'm wrong, it's about 28 hours of research time that you have on the telescope?
Yes, approximately. Yeah, it's something
we have. First light is somewhere in June. Is that correct?
Well, in June, cycle 1 will start, which means all the signs that astronomers propose will be observed in June 1st. I mean, if everything goes well, right? But in the next months, I mean, between February till May, there will be calibrations and they will observe objects for the guaranteed time observation. So some groups that develop instruments, they will obtain their data first.
Okay.
Yeah.
And when do you when does your time start? When do you start to be able to get results from your research on the, from data collection of the James Webb.
So as you mentioned, I have two projects. One of them is part of cycle 1. So for that, we have to wait until cycle 1 starts on June 1st. So the earliest would be June 1st for that project. And that's the one that is related to gravitational waves and black hole mergers. But the other project that I have is a prototypical active supermassive black hole that is called, the galaxy is called NGC 4151. And there I'm part of a collaboration that has guaranteed time. So those observations, if everything goes well, they could take place as early as March, April this year. So if everything goes well, and I'm very excited about this, I will be able to get some JWST data in April.
Outstanding. We'll definitely have to have you back for a follow-up presentation once some results are in. Okay. Yeah. So I'm just looking in the chat here.
Yes, orbit counts too, right? As a telescope on the right side of the sun for what you're trying to observe.
Yes. So the telescope is always facing away from the sun and the earth. So that's what I said, that it will be an unobstructed view of the universe. And as you know, in the L2, the orbit of the telescope is going to be almost the same as the orbit of the Earth, so 24 hours. So we can plan for observations in a very efficient way.
I got a question here. Why does the telescope point roughly parallel to the plane of the sun shield rather than perpendicular to it?
You mean the animations that I show? Well, yeah. So the telescope, is going to see, of course, I don't know if it will be able to rotate in space. I don't think it will be able to do that. But of course, it's looking above the sun shield. So, like I said, I don't know if you will be able to rotate and then look at many places. But in any case, we will be able to see wherever it is located at one specific moment in time. It will have an unobstructed view from the Earth and the sun shield.
Okay. So correct me if I'm wrong. If this is the sun, the bottom of the telescope is here, and then the primary mirror is here, correct?
Yes.
All right. All right. Does counteracting the solar wind require a lot of propellant?
That's a very good question. And the answer is yes. So this is one of the advantages of being in the L2, that naturally, like I said, if you put the telescope in any other part of the solar system, it will just change its orbit. It will lose angular momentum, and you will need propellant to always keep the telescope in orbit. But thanks to L2, we don't need to do that. But there will be still some processes like solar wind that can affect the orbit of the telescope. Now, L2 is a very stable orbit, so hopefully some of these perturbations will not affect much the orbit of the telescope, but some of them will certainly do. And that's why there is propellant and fuel on the telescope to move it to its correct orbit. So the answer is yes, it affects. The exact amount, I don't know. I won't be able to say some numbers, but it's something that is planned. And that's why there is enough fuel for that.
I would imagine they would have had to design for that, because essentially the sun shield is a big light sail, right? So you got to constantly be tweaking it and maneuvering it to keep it in position. And that's going to require propellant.
Yes.
So that's an interesting question.
Yes.
Here's a natural question for many people in our group. They want to know if they can see it through their telescopes at an observing session, just like they could see either the space station or possibly the Hubble Space Telescope. So is JWST so far away that we will not be able to view it from Earth through one of our telescopes?
Yeah, I don't think we'll be able to see it with our telescopes.
Even my 20-inch Dob, I won't be able to see it at a Burton's dark sky observing session. That'd be pretty cool to show somebody. Probably
Yeah,
not,
but
though, huh?
no, it's not possible. You know, well, probably you know this, but JWST is not the only telescope that is on the L2. So there are other NASA missions and other telescopes there. So yeah, I mean, yeah, it's too far away. We cannot see them from Earth.
It's considerably further away than the moon is. The moon is pretty far away.
Yes.
Okay. Let's see what else we got here. Oh, he was talking. We have a question here about mass falling into a black hole. When mass falls into a black hole, is the energy released equal to mc squared?
It's a fraction of mc squared. So we don't know exactly. I mean, there are simulations, there is theory, and some observations confirm the simulations that suggest that the typical fraction of mc squared is 0.1, so 10%.
10%. Okay.
Yeah.
Wow. Now those jets that are being propelled out from the supermassive black hole at some of these galaxies, those are at relativistic speeds, correct? I mean, those jets are close to the speed of light.
Yes, they are close to the speed of light. I mean, a fraction of the speed of light. Yes. And those are created by magnetic fields. I mean, charged particles moving in the accretion disk of the supermassive black hole.
Yep. JWST will remain in the Earth's shadow with respect to the sun, and that was intentionally done. I would imagine it will remain difficult to view from Earth's surface. Yeah. Let's see here. Just some interaction. Anybody have any other questions while I'm going through the chat? Feel free to unmute yourself and just verbally speak. We'll just kind of open it up now. And if you have any other questions.
Yeah, I had a question about, you're talking about observing gravity waves from the merger of supermassive black holes. And I just wonder if you're collaborating with LIGO in any sense to kind of coordinate those observations?
Yes. Okay. So, I mean, my project, we are not going to observe or detect the gravitational waves. That's a completely different field. But the other important thing to mention is that right now with LIGO, we cannot detect gravitational waves from supermassive black hole mergers because the frequencies are very different to the frequencies that LIGO uses right now. So it's basically impossible to detect these right now with LIGO. And that's why this is a very controversial and hot topic in astronomy right now, because we do not have a gravitational wave observatory that is capable to detect gravitational waves from supermassive black holes. Now, having said that, of course, there are many groups in the world that are working with predictions and simulations of supermassive black hole mergers, and they try to predict what is the amount of gravitational waves produced. So the answer is yes, I'm working with some of those groups. I have several collaborators. One of them is in the University of Florida, another one in Yale University, and they are doing these simulations.
Is the frequency higher?
Oh, it's lower.
That's what I thought, lower, yeah.
Yes.
Okay.
Which of the instruments on the James Webb will you be using to study these supermassive black hole mergers?
Yeah, that's a very good question. Thank you. So remember I mentioned we have 4 instruments, NIRSPEC, NIRCam, MIRI, and NIRIS. I am going to use for my 2 projects NIRSPEC. And for me, it's the most important instrument on board of JWST. And the reason is because NIRCam, I mean, it's a camera. So we will get very beautiful images, like I said, very good sensitivity and resolution. But the new things will come from the kinematics, the spectroscopy. So with spectrographs, we can create those maps that I showed and see how the stars, the gas, the dust is moving. And that's going to be revolutionary, in my opinion, that we will do this for the first time from space, because we can do this from the ground. And that's the paper I showed, my Nature paper from 2018. But we have never done this from the ground, from space. So I'm sure, I mean, not only my research project, but many people are very excited to see the results from NIRSPEC. Now, NIRSPEC, as the name indicates, a spectrograph that work in the near infrared. And in the near infrared, we have many species of gas that we can study. That's why it's very attractive. We have molecular gas, we have ionized gas, we have highly ionized gas, etc. So we have many species that we can study, and it's an instrument that we call, it's an integral field spectrograph. It means that it can create those maps that I showed. It's not just a spectrum of the galaxy like it was in the past. We will have coverage of all the two-dimensional field of view that we are observing. So that's why it's a very powerful instrument. And that's the one I'm interested in using, because I want to study the two-dimensional kinematics of the galaxies.
Thanks. I wish you lots of good luck. This was great.
Thank you. Thank you very much.
Very exciting. Will you be able to receive your data and research in Memphis, or will you need to travel to another station?
No, I can work here in Memphis. So basically how it works is that, I mean, I can imagine it will be the same as in Hubble. So the Space Telescope Science Institute is in Baltimore, and they receive all the data. And they have astronomers, or they have data scientists who process the data, and they work with the raw data, and they give to the astronomer the final product. But you can be located anywhere in the world, even. I mean, with Hubble, you could, I mean, if your proposal was accepted, you will receive the data. It's online, so you just download your data and you can work in your office or at home or anywhere.
Nice.
Yeah.
How long does it take to get the data, though?
Well,
I would imagine the data sets are pretty large, right? Several terabytes?
Yes. So like I said, the Space Telescope Science Institute, they receive the data. As soon as they receive the data, they start working on that. I mean, they have a lot of people working on that institute, and they just start processing the data. So it takes a couple of days only. So if your object is observed, then they process the data, and they tell you, they always send you an email. They say, we have observed your galaxy this day at this time. And then 2 days, 3 days later, they say, you can download the final product at this site.
Yeah.
Yeah.
Yeah, it's just really, you know, when you think about this in context, 30 years ago when Hubble was launched and the internet was essentially in its infancy. I mean, the internet back then was essentially still the ARPANET. And you think of the evolution not only of our knowledge, but of the capabilities that we have technologically today to gather and share and archive data information. Just really extraordinary. So one question I had, you know, the James Webb Space Telescope is going to be looking at a portion of the universe that's so far back in time that essentially my understanding is that the visible light from when those galaxies was created is going to be stretched cosmologically to the infrared portion of the spectrum, and we'll be able to detect that. And I know a big part of your research, to oversimplify it, is the chicken and egg argument of the supermassive black hole versus the galaxy formation. So can you talk about what you kind of hope to find in that cosmic dark ages by looking at the earliest galaxies in the universe that may give us a better understanding of the evolution of galaxies?
Yes. Well, I mean, first I want to confirm what you just said. So that's one of the reasons why this telescope works in the mid-infrared, because the light from the distant galaxies is redshifted to mid-infrared wavelengths, not even in the near-infrared. So when people designed James Webb, they had this in mind, and they said, well, if we're going to observe light from redshift 100, we have to have an instrument that works in the mid-infrared. I don't know the exact wavelength, but it's certainly more than 5 microns or something like that. So those are the very distant galaxies, the high redshift galaxies. Now, there are many open questions there. So actually, I'm not an expert in high redshift galaxies. I study more nearby galaxies where we can do a detailed mapping of the kinematics and other properties. But there are many open questions for the first galaxies. I mean, one of them, one of them that we see right now is related to the presence of very massive, supermassive black holes. So some of the most distant quasars that we have detected, they have black holes that are billions of solar masses. Some of them are the most massive black holes in the universe. And that is not consistent with our current understanding of galaxy evolution, where supermassive black holes grow through interactions with other galaxies, and they need millions or billions of years to grow to the sizes that we see them in nearby galaxies. So the fact that we see billions of masses in quasars that are at very high redshift is something that we don't understand very well, how those black holes grew to those masses when they had less than 1 billion years.
Right.
Yeah.
Yeah, I mean, our Milky Way galaxy is pretty big compared to the other galaxies in our local group. Obviously, Andromeda is bigger, but yes, our supermassive black hole is what, about 100 million solar masses or so? And it's been cannibalizing other galaxies for 10 billion years or so. And yet it's pretty small compared to some of these supermassive black holes that, yes, you're seeing at the very edge of the observable universe. So how do they get to be so big, billions of solar masses, when ours is only 10 million or 100 million solar masses or so, and it's, yes, supposedly been around for 10 billion years or so?
Yes, exactly. Exactly. This is something, I mean, for the Milky Way, that we do not understand very well the mass of our supermassive black and how it was formed, actually. There is no real accepted hypothesis for the formation of the supermassive black hole in the Milky Way. Because like you said, it's not that massive compared to black holes in just the Andromeda galaxy. The black hole in Andromeda is, I think, 100 times more massive than the black hole in the Milky Way.
Yeah. If there are any other questions, just go ahead again, either chat or unmute yourself. I'm getting several people commenting. Excellent presentation. Thank you very much. It certainly was. This was a fantastic presentation. Is it an oversimplification that if two supermassive black holes merge, that the mass of the resulting black hole is just the sum of those two masses? Or is there something else going on physically there?
Well, there is something else going on, and the math can be very complicated, but it turns out that even if you do all the equations and all the math, you compare the number that you obtain through all those calculations and what you would just do by adding the two masses, and the number is very similar. So in the field, it's accepted that when you add the two masses of the two supermassive black holes, you say that the resultant or the final black hole will have that mass. And it's a good approximation.
Very similar, man. Oh, they just brought me dessert. Thank you very much. I appreciate you guys going to bed.
Olaf special.
Yeah.
Hey.
Olaf special. I'll be done in a second.
I have a
talking about black holes.
I have a non-science question. We really appreciate you being in Memphis. It's terrific. You're part of the department. And anything about your personal story of getting to...
Yeah, sure. Yeah, so, well, before coming to Memphis, of course, I was a postdoc. So I had actually 3 postdoctoral positions after I graduated from my PhD. So like Jeremy mentioned, I did my PhD in Germany. And then I moved to the Canary Islands in Spain. That was my first postdoc for a couple of years. And then I had another postdoc at the University of California in Los Angeles. And then I had another postdoc in Colorado at the University of Colorado Boulder. But at some point in my career, which is the same for many astronomers or scientists, you want to find a permanent position because all these postdoctoral positions are temporary. So it's great because you meet a lot of people and you can just do science and it's fun, and it's also good to live in several places. But at some point, I mean, that's my case, and the same for many of my colleagues, probably comes with age. You want to settle down somewhere. So at some point in my career, I started to look for a position like the one I have right now in Memphis. So it's a research professor position where I can do research and teach. And I love doing both of them. So as you can see, I love the research that I do, but I also like teaching and mentoring students. I think it's something very important for us to motivate new generations to study sciences or go into the STEM fields. So I enjoy teaching, and I like to always provide examples of my research or things that I think are interesting. And I see the faces of the students or something come to me and they say, that was very interesting. I like it. That motivates me a lot.
Superb.
So I was looking for a position like the one I have where I can do research and teach. And at that moment, the University of Memphis were looking for an astronomer. And I thought it's a perfect place for me because I can start a group there. I can design the astronomy program the way I think it should be done. And I see a lot of potential here in the community and with the students and the people interested in astronomy. So, and like I said, I mean, for my research, I can work anywhere in the world. So that's great. It was a very good opportunity for me.
We're fortunate to have you.
Fantastic. Fantastic. Thank you.
Glad to have you.
Yeah, absolutely. Fantastic. To kind of wrap up here, we're getting close to 10 o'clock and we don't want to keep you on too much longer, but do you want to talk about some opportunities that you have for any students who are interested in getting into astronomy and astrophysics? And you're building this program at the University of Memphis. This is a very exciting area of research, and there's going to be several breakthroughs coming. So any final thoughts on that?
Yeah, so this is actually related to what I was just saying, a continuation. So I have been here for 3 years, and I think in this time, I mean, I have been establishing some collaborations like the one that I mentioned at the Pink Palace. Now with the Memphis Astronomical Society, I hope that we can continue having these presentations and these talks. And like I was saying, at the University of Memphis, we have programs for both undergraduate and graduate students. And right now, I think the most important astronomical project in the world even is working with JWST data. So for the young generations, if they have the chance to work in a group where they have JWST data, it's going to be fantastic for the future. And that is something that we have here in Memphis. Now, we do not have only that. I mean, as I said, I think it's the most important, but we have other projects that involve ground-based telescopes. So in my career, actually, I used ground-based telescope for many years. And that's one of the reasons why I lived in the Canary Islands and in UCLA, because we had access to telescopes both in the Canary Islands and the Keck telescopes in Hawaii. So I was traveling to Hawaii, I don't know, 5 times a year when I was at UCLA. And I collected a lot of data. So we have a lot of data that is just sitting there and that is waiting for a creative and motivated student to just take the data and work with this amazing data from active supermassive black holes and galaxies observed with the best ground-based telescopes in the world. And finally, we also have other projects that involve other space telescopes or NASA missions, like the one you see right now in this slide, in my last slide. We have a photograph, a picture of the SOFIA telescope, the Stratospheric Observatory for Infrared Astronomy. And that is a very interesting project. As you know, it's a telescope that is mounted on a modified airplane. And this telescope works in the infrared because we want to fly above certain altitude on the Earth to detect infrared light or so that we are not affected by the atmosphere. And I had the opportunity to fly on SOFIA, and some of my students had the opportunity to be on board of SOFIA. So you fly at higher altitudes, I mean, the stratosphere, and it's a very interesting experience. So we collected data from SOFIA, and we have more data coming and maybe more opportunities to fly on SOFIA or to go to other telescopes around the world and collect data. So I think these are all very exciting things that we can do here at the University of Memphis. But in addition to that, I just would like to say that doing a program in astronomy, either undergraduate or graduate even, provides a lot of skills that people maybe are not very much familiar with all the things that you learn in this field. And I think it's very attractive because I think studying space and the universe is fun and attractive and exciting, but it also includes, of course, astrophysics and understanding the laws of physics of the universe, but other skills like data analysis or data processing or data reduction. And that is something, I mean, programming skills. These are things that you will use or students will use in their future careers, even if they abandon astronomy at some point. These are things that can be used for many areas in the industry, in the private sector, or in the government.
I think your students need to practice their presentation skills by making presentations to the Memphis Astronomical Society.
Yes.
That's a shameless plug right there. We're always looking for speakers. So
yes. I see a question right now. It says, where does SOFIA launch from? It launches from, it's in California. I forgot right now the city. It's near Pasadena, but it's still north from Pasadena. Palmdale. Yeah.
Edwards Air Force Base?
Yes, there is well, when I was there the first time, I was surprised because it looks like a cemetery for NASA missions that are not used anymore. So you visit that area, I mean, it's a huge area, and you see a lot of airplanes or vehicles or helicopters. And I think they are not used anymore, but it's there in Palmdale.
Understand. Thank you.
Mm-hmm.
Excellent. All right, wrapping up. Any other thoughts, questions, comments?
Thank you very much. This
Thank
is
you
an excellent
again.
presentation.
Once again, thank you so much.
Yeah,
yes,
thank you for having me.
Bravo.
This was fun. Thank you. Okay.
All right, just to wrap
everyone.
up here, I'm just going to share my screen and just a couple of brief things here.
Jeremy, can I make
go
a
ahead.
plug for the Memphis Astrophotography Group? We'll have another Zoom meeting Saturday evening, the 15th, starting at 7 p.m.
Okay, excellent. So that's next Saturday, a week from tomorrow, again, around the time of the full moon. So we'll send an announcement out about that. Forgot to mention that. So thank you, Rick. If you're interested in astrophotography, we'll get our focus group. We'll have another meeting next Saturday, the 15th. So
Jeremy, this is Bill. Are you at a ski area, or is that an outstanding background?
that's my cabin in the mountains. No, that's just an outstanding background. I'm looking for a good winter trip. Just haven't had the time yet. So
tell us about your dessert.
Oh, so yeah, my stepdaughter, whatever you want to call her, she likes to basically just take a bunch of things, mash them all up and throw them in a cup. And then I'm not even sure how to describe this.
Hey, it's Jeremy, share it.
Strawberry ice cream, M&Ms, Snickers bar, and then also Reese's peanut butter cups, which I'm a sucker for.
Yeah.
So in other words, high calories in a fancy Olaf cup.
We need to give that a name.
Yummy.
I'm sure I'll think of something creative. So yeah, anyway, interesting. Well, thank you again, everyone, for joining this meeting. Special thanks again to Dr. Muller Sanchez. If you'd like to learn more about the Memphis Astronomical Society, again, check out our website, memphisastro.org. You can find us on Facebook as well as YouTube. And of course, you can join us both on our website and by going to, or by going to joinmas.com. So with that, we'll kind of wrap up. Again, I want to thank everyone for coming out. And again, if you're a young person watching this presentation, you're in junior high, high school, or even younger, and you have a passion for astronomy bordering on addiction, there are opportunities right here in the Memphis area. So we can help you. We can get you to the right people. Our local universities, the University of Memphis, Rhodes College, always looking for students. Dr. Muller Sanchez is building the astronomy program there. Very exciting research. I mean, this is groundbreaking stuff, guys. 28 hours of research time on the James Webb Space Telescope. I mean, we're on the cusp here of, again, another breakthrough in our understanding of the universe. So this is a very exciting time to be in that field. So keep that in mind. You don't have to travel to the other side of the world or the other side of the country. We got opportunities right here in Memphis. So we would certainly love to help you out if you're interested in those fields. So again, with that, we'll wrap up. Thank you again. Happy New Year to everybody. And we will see you next month. Good night.
Happy New Year, everyone. Bye.
Bye. Bye-bye.